ನಮಸ್ಕಾರ ಮೇಡಮ್.
ನಮಸ್ಕಾರ ಸರ್.
ಕೇಳಿಸ್ತಾ ಇದೆಯಾ?
ಕೇಳಿಸ್ತಾ ಇದೆ ಸರ್. ನಾನು ಮಾತಾಡೋದು ಕೇಳಿಸ್ತಿದೆಯಾ?
ಇವಾಗ ಕೇಳಿಸ್ತಾ ಇದೆ. ಓಕೆ,
ಕೇಳಿಸ್ತಾ ಇದೆಯಾ ಸರ್?
ಈಗ ಕೇಳಿಸ್ತಿದೆ.
ಓಕೆ. How are you, sir?
I'm good, madam. Thanks. How are you?
I'm fine. Check how many have joined. Okay. 215 ಅಂತ ಹೇಳಿದ್ವಲ್ಲ ಸರ್. ಐ ಥಿಂಕ್
ಅದೇ ಸ್ವಲ್ಪ ಅದೇ ಇಲ್ಲಿ ನೆಟ್ವರ್ಕ್ ಇಲ್ಲ, AS ನಲ್ಲಿ ನೆಟ್ವರ್ಕ್ ಮೊಬೈಲ್ ಮಾಡ್ಕೊಂಡೆ, ಅದು ಪ್ಲೇಸ್ ಫೈಂಡ್ ಮಾಡಕ್ಕೆ ಇದಾಯ್ತು.
Is that okay sir now? ಇವಾಗ ತೊಂದರೆ ಇಲ್ಲಲ್ಲ?
I think so. ಚೆನ್ನಾಗಿ ಕೇಳಿಸ್ತಾ ಇದೆಯಾ ನಿಮ್ಗೆ ಈಗ?
ಕೇಳಿಸ್ತಾ ಇದೆ. No problem.
Okay, so I think it should be.
I think we'll have to wait for 5 minutes, sir.
No problem. ಆಯ್ತು. ನಾನು ಲೇಟ್ ಆಗುತ್ತೆ ಅನ್ಕೊಂಡೆ, ಬಟ್ ಐ ಆಮ್ ಏಬಲ್ ಟು ಫೈಂಡ್ ಆನ್ ಟೈಮ್. ಬಟ್ ಇಟ್ಸ್ ಫೈನ್.
Okay sir. No issue. Hello, good afternoon to everyone. Am I audible to you?
Yes, ma'am, you're audible.
Thank you. So, a very good afternoon to one and all present here who have joined for this webinar, and warm welcome to all of you. So, today we are in the second day of the 3-day webinar, and as you all know, we are celebrating the birthday of the legendary mathematician Srinivasa Ramanujan, and today's resource person is Dr. Devaraju N, and who is a postdoctoral researcher in the Department of Geosciences, University of Oslo, Norway. He will be speaking on the topic application of mathematics in global climate modeling. I welcome Dr. Devaraju N for this session. Thank you very much, sir, for accepting our invitation and joined us to enlighten us in the application of mathematics in global climate modeling. I request our coordinator, Mrs. Mala Shri, to introduce today's speaker to the audience. Mala Shri, over to you. Mala Shri.
Hello, good afternoon, everyone. Uh, I'm honored to introduce Dr. Devraju N, our speaker for the session. As a tribute to the mathematical genius, Sri Srinivasa Ramanujan, on his birth anniversary, Department of Mathematics is organizing a 3-day webinar on innovation in mathematics and usage of modern tools. I'm honored to introduce our speaker for the session, Dr. Devraju N, postdoctoral researcher, Department of Geosciences, University of Oslo, Norway. Dr. Devraju N obtained his degree and master degree from Bangalore University and received his PhD degree in the field of applied mathematics from Bangalore University. Sir has rich experience as postdoctoral researcher and project scientist, and also scientific researcher from Indian Institute of Science, India. Dr. Devraju N has received a CNRS Grant Award for the participation in European research course on atmospheres in Grenoble, France. He also has received Grant Award from International Council for Science and Institute of Mathematical Sciences, National University of Singapore. Dr. Devraju N also has reviewed research papers for several journals. And also, Dr. Devraju N has published several papers in the reputed journals. A warm welcome you, sir, for this session. I would request Dr. Devraju, sir, to take over the session. Thank you. Thank you, and welcome once again. Welcome to all the participants.
Sir, we are not audible, sir.
Oh, yeah. Okay. Sorry.
Yeah, now it is fine.
Oh, okay. Yeah. Thanks, Malashri, for introducing. and also thanks for the head of the department for welcoming to give the invited talk. So I'll try to share the screen first. You can see the screen. Can anyone confirm?
Yes, sir.
Do you see the screen?
Yes, sir, it is visible.
Okay. Yeah. Once again, yeah. Thanks and thank you all for joining. I hope many of you have joined, more than 30 or 30 plus. I have given this talk actually already in like Ambedkar Institute and in Coimbatore. Maybe some of you may have attended, and it may be repeating. But yeah, so anyway, so I'll mostly talk about application of mathematics, but not really the mathematics itself. So I'll just show the equations which are used for studying the global climate model. So yeah, I'll first introduce what is global climate modeling, and then focus on real world applications of global climate models, and then few takeaway messages from this global climate modeling. Okay, introduction to global climate modeling. So yeah, mainly what is a global climate model? So a global climate model is a complex mathematical representation of the major climate system components like atmosphere, land surface, ocean, and sea ice, and their interactions. So I hope you can see also my cursor here. So yeah, so if you just take any point, any grid cell on Earth that is divided in a global climate model into several components, like as I said, atmosphere, this is the atmospheric component, and then land, you have the surface, and then also ocean actually. So even mountains are represented. So, but I'll not go into details of all this, but maybe I'll try to focus on land and atmosphere interaction applications, and maybe some few applications to the oceans. So yeah, basically global climate model is a mathematical representation of the major climate system. How the global climate models evolved. So it started in mid 1970s. People started modeling or writing the equations, mathematical equations for the only atmosphere. Like I hope many of you studied fluid mechanics. So if you see, it's mostly the how fluid flows model, like using Navier-Stokes equations to solve the flow problems. So yeah, that's what they started with atmosphere, and then started combining, like introducing the land surface, how the land surface interacts with the atmosphere, like trees, for example, how the trees interact with the atmosphere. And then in early 90s, so you have atmosphere, land, and then ocean interactions, ocean and even sea ice. So they have introduced in late 1990s. This is early 1990s, and in late 1990s they try to introduce the like sulfate aerosols, like dust particles actually. So in like sulfur cycle model. Basically, sulfur is nothing but the dust particle, which it's a chemical contains in the dust. And then in early 2000s, so again, like non-sulfate aerosols, carbon cycle, they have introduced like land carbon cycle, like soil biogeochemistry. In soils in the land, you have soil, and then almost like carbon, which is in the soil. So they started how the carbon, which is moving from soils to trees and then to atmosphere, and then again going back to the soils. So that is called the carbon cycle. So they have introduced this. chemistry. And then in 2010 onwards, actually they started introducing also like dynamic vegetation. That means how the trees grows with changing the environmental conditions. For example, rainfall, humidity, so on. And then atmospheric chemistry, that is like interactions between the chemicals in the atmosphere, how that is affecting the atmosphere and the climate, even in the land carbon cycle, how that affects. So they started introducing, and I think in recently also they have really complex climate models. So this image I have taken from, I think, Canada, like CCNIN website. So it's not updated. So just to give an overview around the world, who does the climate modeling? So if you see in North America, so this is where here, United States, most of the climate models, these are the dots, which are the climate modeling centers. So around like five or so in the United States itself, there are climate models. In Europe, there are several global climate models. And in Norway, where I am there, that is NORESM, Norwegian Earth System Model. So that is one of the important global climate model. And then previously I was in France, where that is, I think, in France it was like IPSLCM, like Institut Pierre-Simon Laplace climate model. This is another major, many people use this model. So these are kind of some of the most used models. And this is another one is like CESM, where I started using this. This is Community Earth System Model. Even when I was in IASC, Indian Institute of Science, we used to use this model. So anyone can download this model and start using it. That is, run the model and analyze the results. But you need like global, supercomputers for this global simulations if you want to do. Or you can also do like point simulations at one point, like just for example, anywhere, one grid cell, like in Bangalore. If you want to run the model and see how the land and atmosphere interacts, you can do that also using these models. So, but mostly I'm now talking about this global climate modeling. So that means you run the model for whole globe. Just to give again what really it contains inside the global climate models, like IPSL, CM in France. So they have, discretized the whole globe in like this. It has shown here. So you can see the horizontal discretization and then vertical discretization up to the atmosphere, the top of the atmosphere, from surface to the top. So you can have a discretization. So the atmospheric model is called the LMDZ. That is, it's a three-dimensional dynamical core model. LMDZ means Laboratoire Modelization Dynamic. It's in French actually. So, and Z stands for zoomed version of the model. So, and for just the land surface, you have like RKD, called RKD. Like it has like soil thermodynamics, vegetation, that means trees, plants, crop plants, and hydrology, that means how the water goes through the rivers and even in soils. So hydrology, and then carbon cycle, how the carbon which is flowing around like soils and vegetation or the plants into the atmosphere. And you have also like glacier model and then ocean models. So yeah, they have like INCA. It's another model which is called chemistry and aerosol microphysics model. So like this, they have several components and which are combined together called the global climate model, and they named it as IPSL-CM. So whole this global climate model you can also run like a single column model. Okay, so again, now if I just go in deeper into the land surface, just alone, only land model, that means you have like several processes like surface energy fluxes. how the sunlight comes down and how it absorbs by plants, and how the reflection. So you have incoming radiation and outgoing radiation, and the changes in latent heat flux, sensible heat flux. These are all represented through mathematical equations actually. So whatever I'm talking about, all these processes, which are all mathematical equations, which I'm just showing I'm just talking about applications, but not the equations. But the behind all these processes, there are equations. And then, so just if you take hydrology, so you have again precipitation, evaporation. So that is water coming into the earth surface and then going to the atmosphere, that is evaporation. And the transpiration means plants transpire the water, so that is also modeled actually. And there are like several flow processes like infiltration, subsurface runoff, water which is going underneath the surface. So yeah, you have all these several processes are represented. Again, this is biogeochemical cycle. That means how the carbon and nitrogen, basically they don't have all the chemical cycles in the soils, but for now they have carbon and nitrogen cycle introduced in this model, like community terrestrial system model. This is a part of like CESM global model, where I showed, which is NCAR from US. So yeah, these are all the details of the global climate model. And this land surface model is also actually part of the Norwegian Earth system model actually. So you have in Norwegian Earth system model, like atmosphere model, land model, and sea ice model, and there are several other like for ocean model different, and then river transport models. These are all combined together, the global climate model actually. So yeah, so whatever I showed before, all those models are really based on these like primitive equations, or you may have called the Navier-Stokes equations, like conservation of mass, momentum, and the heat transport. So you have just to give an example actually. So but different models consider different form of equations and solve them numerically. Okay, so this is to show that mathematics is really so is the behind these global climate models. Just sorry to I'll come back again. Okay. Yeah, so just to continue again, if I want to show biogeochemical cycles within the land model, so you have these processes, even root processes. So like photosynthesis, how plants take up CO2, and then again how the mineralization of the nitrogen, and even the roots, so plant roots, how they decompose and then release the chemical, right? So it's all actually represented in different form, like so you have plants which are leaves fall into the ground like litter, it's called a litter. And then so you have different litter pools. So some leaves decompose fast, some may decompose slowly. So like this, they have several pools, like slow pools, slow soil carbon, fast soil carbon pools. Like this, there are like equations you see here. This is the concentration diffusion thing equation. So how much carbon which is going in and coming out actually. So this is the input, and this is the output actually, what is going into the, like for example soils and coming out of the soil. So Ri, this is the input and output, and this is actually the transformation between different pools. Like this, it is showed like litter from litter 1 to litter 2. So how the decomposition happened between litter to soils, you see that. So these all small processes are also represented actually. Okay, so again, this is to show that the global climate models require supercomputers. This is the, I think, I have taken example of a Cray XE40 supercomputer. This is in Indian Institute of Science, and which is called as Sahasrat. And this supercomputer is capable of 14,000 trillion calculations a second. So, I mean, yeah, you need, if you want to run a global, like for the whole globe, the models, so you need really the big supercomputers, and Fortran and C language. So yeah, just to, I mean, to tell that how these global climate models are used, and so what they can really tell us, what these global climate models can tell us. So yeah, I just listed here some of that. That is, global climate models enable us to improve the understanding and prediction of atmosphere, ocean, and climate behavior. And then the climate models allow us to determine the distinct influence of different climate features by providing a way of exploring climate sensitivities. That means how sensitive climate is for, like, CO2 emissions, or deforestation or afforestation. And again, the changes can be made to one feature in a climate model to discern the impact those changes have on the climate. So maybe this sentence may not be easy to understand, but what I meant was, like, if you want to really look at only like CO2 effect on the climate, on temperature, on the rainfall, so then you can really separate this effect, because the climate system is really combined, everything is connected. So by doing the experiments, you cannot really tell how the CO2 alone is affecting the climate. But so through the climate models, you can really quantify how the changes in CO2 can affect the climate, or changes in nitrogen fertilization, for example, or CO2 fertilization. So, and then you can predict the future climates, such as global warming trends, using current or historical data as a basis. So here is one example for the global surface temperature change, which are simulated by all those climate models. As I showed, like, there are many climate models. So if you see this spread here, the gray color, which is the spread based on different climate models, and the black line is mean of the climate models. And yeah, so this is for the historical period from 1950 to 2015, how that global temperature has changed relative to 1850, like pre-industrial period. So you can see that the temperature is warmed about 1 degree in 20 I think in the current up to current year, or like 2020, if you also take, it's about 1 degree. And then for future, like, you can predict up to 2100. So if we really allow all the emissions without any like mitigations, without any electric cars, or electric, if you don't want to go, so so then it is like as usual scenario. That means, so you don't want to do any mitigation, you don't want to plant trees. If you don't do anything, then so we really may reach about 5 degrees. But if you really control, like planting trees, not only that, but reducing emissions like CO2 emissions, so you can really control the temperature by 2100, like about like 2 degrees or 3 degrees. Based on, these are all based on different scenarios, how the humans or the politicians all over the world take the decisions. These lines are depends on that, actually. So yeah, again, the main question is, do we really believe these global climate models are really based on equations and many assumptions which are involved in the equations? So, but how good they are? So if you just see here, the black line is the observed climate, like temperature change in the historical period from 1850 to 2020. And this other maybe the yeah, this color actually. So here, which is from the simulated model. So, and the spread again, spread is from different climate models. So, I mean, if you take one model, that may not be accurate, but if you average out all the models, then you can see that this line is close to the block line. So that means the models are reasonably simulating the climate actually. So it may not be like exact, like not 100% right, but they do give us the I mean, some clue of like how the climate is evolving. So you can like believe that in the future, whatever this model predict, that may happen. So again, to give some real world applications of these global climate models. So again, I just want to repeat that, and so I'm not really going to talk about equations itself, but the application of these equations, mathematical equations. So yeah, just this is one of my research papers published actually when I was in India. I have worked on how the deforestation affects the climate, like rainfall. So I just wanted to introduce that. Yeah, by near like 1750s, humans deforested around already like 7% for the agricultural land, like for cultivation. That means they have, yeah, I mean, removed at that time itself all the around 7% of the trees over the globe. And in the present day, it's nearly 50% of the ice-free global land area is covered by only crops and pasture lands. So that means you imagine it's all that all the trees are cleared by around 50%. So, and then, yeah, you have nearly 23% of the anthropogenic CO2 emissions is from this deforestation or like agroforestry and land, yeah, other land uses. So AFOLU means it's agroforestry, other land use. So yeah, this is really about 23%. It's really huge, which is contribution from this land, land use, land cover change. So what I mean was you are changing the landscape, and that is affecting. I mean, yeah, that is affecting the climate through CO2 emissions. So yeah, here I just provide a slide to tell that. So if you have more trees, then you have more precipitation. That is like, and high evapotranspiration and more precipitation. Then the climate will be cool and wet, you can say. And then this process continues. If you have more trees, you have more rain again. So you have more trees. This is kind of a positive feedback. So like I call trees means like vegetation. You have, and then atmosphere is in, yeah, in the atmosphere you have clouds. So this is the interaction between vegetation and atmosphere. So that means you have more trees, more evapotranspiration, more clouds, and then more rain. So land is really interacting with the atmosphere. So that's what this means. This is yeah, it's called like wet becomes wet. So if you have more trees, uh, more rain, and then similarly if you have drier climate, then it becomes dry, and maybe ultimately one day it may become desert. So these are like again positive feedbacks. So since we have now cleared about 50% of the global land area or global forest, so if we really, so what this can affect, will this global land, will it become like dry or wet? I mean, so if you want to understand that, so these global climate models can really help us to see how the global climate in future can change if we really remove like 100% trees. So yeah, this what the some of the few questions I try to answer here. Like if deforested areas are abandoned and forests are allowed to regrow. So that means if like there are like 50% of forest is removed, but if you plant all those trees which are removed, will the climate comes back to the normal state or to the pre-industrial state. So if it is coming back to the normal state, but how long will it take for the climate system to reach? So these are the questions I tried to address in my one of the research paper. So it is published in Biogeosciences. This is really long ago I published. I mean, yeah, this is one figure from this paper actually. So this blue line is the control climate. Like if you have a pre-industrial, like 1850 conditions, before all the industries comes, the climate was like this, blue. So it is stable. If it is like, so y-axis is the temperature in Kelvin, and the x-axis is like the number of years actually. So this is the model, global climate model simulation, and this, the temperature is global climate mean temperature actually. This is global mean. So blue is just without change. So the red is like I have removed like the trees over the globe 100%, and then allowed the trees to grow back. So you see that the temperature is really going back to the normal state like blue, but it is really taking time to go back. So if I just allow here trees like in and at the under here, so that trees start to grow back, and then the temperature also is going back, but it does not go to the blue line immediately, but it takes several like 200 years you see here, and 300 400 years. So even, yeah, around more than 500 years are required to reach the normal state. So this is one of the result from this paper. So if you want more details, you can just search and download this paper, which is freely available for anyone. And similarly, this is the rainfall actually. So yeah, I'll try to go for first. I think I'm taking more time here. Next. So yeah, this is to show the global map, how the temperature, since this is a global model simulation, so you can see that even over India also, how the temperature has changed in global deforestation and the rainfall has changed. So yeah, maybe I don't focus on this. The main message from this is that, so if you allow the trees to grow back, and so only the 11% change over the globe, 11% of the grid cells are like significant changes, but otherwise it goes back to the normal climate. Maybe this is a bit maybe complex, but yeah, I'll skip this. Okay, maybe this figure may be useful to understand. Like the tree cover fraction means on the global land, how the tree, when we allow all the trees to grow back, so you see that the tree cover fraction in the global is really slowly going back, and it takes, I mean, the trees take several years to, I mean, to be matured. So there are some trees in high latitudes which keeps on growing, like even after 800 years actually. So this is x-axis is years. So this is 1,000-year simulations actually. That's why I show here. So 1,000 years on the x-axis. And this is like tropics. I divide the globe into tropicals and mid latitudes and high latitudes. So in tropics, like in India, most of the trees mature quickly, like within maybe 50 years or 100 years. For like from, yeah, you see that from 100 years to 200 years, all the trees are like almost gone or grown back to the normal state. But in high latitudes, like in Norway, so because of the cold climate, the trees that really takes time to grow back. And so even after 1,000 years, trees have not yet matured completely, like they still grow. And then, yeah, this is another application of the global climate models. Again, using those global climate models, I have studied and I published the paper, which is in PNAS, which is called Proceedings of National Academy of Sciences. And yeah, basically from this paper, we have focused on the rainfall over the globe, but also on India. We focused on specifically over India also, but on global scale also. So yeah, the main question is, how does deforestation affect rainfall, especially in the tropics, like for example in India? And is there any fundamental constraint that govern the monsoonal precipitation changes? So we try to address these questions in this paper. Okay, so this is again to give one basic idea of to understand the results actually from my previous paper. If we want to understand the results I'm going to show in the next few slides. So you need this, if you search on the Wikipedia page, you may find this figure actually. So this is called the ITCZ, Intertropical Convergence Zone. So you see the yellow band actually here. So where yeah, so if you just keep seeing, I think in July, if you see here in July, this band will be closer to India. So that means from July to September, actually this band will be closer to India. This is an intertropical convergence zone, and in a, I mean, layman word, you can say it's a rain band actually. So this brings the monsoon actually for India during the like July, yeah, July, August, September. So this is the main reason you receive more rains in India. So yeah, as season changes, like in December, it is away from India, so that's why you don't have much rain. But even in September, so you have more rain because this is closer. So just keep this in mind to understand the results I show in the next slides. Okay, so this is the result from this global deforestation simulation. So where again, so this is the community earth system model I showed, I think in the previous slides, where this model is developed at NCOR, and I have run the simulations to understand the deforestation effect. If you remove the trees all over the globe, and then so you see that the rainfall, the precipitation is nothing but actually rainfall actually. So so the blue color means here the blue color is actually reduction in rainfall. If it is red, then it is increase in rainfall actually. So you see the scale here. This is about 1 millimeter per year, the unit. Oh no, millimeters per day. This is actually, and this is the change. So the change globe, yeah, this is the yeah, the rainfall unit actually. So the rainfall here, which is shown, and you see that all over the northern hemisphere where there is most of the land and most trees are there. So when you remove all the trees, there is a large decline in rainfall. So even over India, so you see that there is large decline in rainfall. And whereas like over Australia, if you see that there is an increase in rainfall. So this is an interesting result that we find. So even though we do the deforestation all over the globe, even in the southern hemisphere, here, even in the South America, and even over Africa, South Africa, here also we remove the trees, but you have the increase in precipitation here. But whereas decrease is only in the northern hemisphere. So yeah, so these are all like different simulations. Like I remove the trees only in the northern hemisphere, only here, and then I try to understand how that is changing the global precipitation or global rainfall. But maybe I'll try to focus on why this is happening actually. So why there is an increase in rainfall here in the southern hemisphere. So even though we remove the trees all over the globe. So Yeah, again, you just see here, these are all different monsoon regions where like East Asia, North America, North Africa, uh, and then Australia, South America, and South Africa. You see that in the left, this is the Northern Hemisphere region. So Northern Hemisphere means you can see here, yeah, from equator onwards, it is Northern Hemisphere. From zero line, you see that here, this line, and then this is Southern Hemisphere. So these are the Southern Hemisphere monsoon regions. You see that during the monsoon season, like June, July, August, like in India also, so you have decrease in rainfall consistently, but in Southern Hemisphere, there is an increase in rainfall actually. So this is change in precipitation y-axis, and this is the season actually, monsoon season. So yeah, maybe I'll skip that. I'll skip this also. So yeah, so here I'll show that the reason for that is, so if you see that in a global deforestation, this is actually the location of ITCZ I showed in the previous slides. This one. So this location actually, so if you do the deforestation all over the globe, then this is actually shifting towards Southern Hemisphere actually. So that's why you have decrease in monsoon in all the Northern Hemisphere, but an increase in monsoon rainfall in the Southern Hemisphere. So because the actual location, if during like monsoon season, like June, July, August, the location shifts when you do deforestation. So now it is going so closer to India. So if you do the global deforestation, it may not really go much closer to India. So that's why, so it keeps into the south. So that's why you have decrease in rainfall here, but there is an increase in rainfall in the Southern Hemisphere. So this is the result, that reason that we find. So this location is changing. So yeah, here you see that about 1 degree, I hope you know latitude and longitude, about 1 degree latitude is changing if you do only boreal deforestation, or if you do global deforestation, this is about 2 degrees, it shifts southward, the ITCZ location, the rain band, you can say ITCZ means it's a rain band, which is going south. So that's why you have yeah, decrease in rainfall in the Northern Hemisphere and increase in rainfall in the Southern Hemisphere. So these are again another reason. We try to look for another reason why that is really happening, why that shift is happening. So because in the Northern Hemisphere, when you do deforestation, there is a lack of energy. So that means that try to draw the energy to balance. So into the Northern Hemisphere, you see this is the plus 90-degree latitude. That means this is Northern Hemisphere and this is Southern Hemisphere. So here you have decrease in net energy flux in the atmosphere, and then it transfers the atmospheric heat to the Northern Hemisphere because there is a lack of energy. So it tries to draw the energy back towards Northern Hemisphere. That's why the location of that rain band shifts. So that is the reason. I think I'll skip this figure. Okay. Yeah, this is to summarize the result of that paper. So basically, if you see this blue line, this is before deforestation. So on like equator, this is the tropics, and this is again Northern Hemisphere, this is Southern Hemisphere. So when you do the global deforestation, so there is a cooling. So remember, I didn't, I think I did not mention that. So in this global climate model, this simulation, so there is no CO2 emission. That means only you are removing the trees and changing the energy balance, but not the CO2 emission. So since we don't consider CO2 emissions, which is contributing to warming of the atmosphere, but the deforestation, because less trees, that means they don't have, so there is no absorption of heat, and that means there is a cooling. So only whatever the sun radiation comes, that goes back because there is no trees, there are no trees to absorb. So that's why there is a cooling. That means in the northern hemisphere there is energy deficit. So because there is more land also in the northern hemisphere, that's why you have more forest area. So that's why there is more effect in the northern hemisphere. So you see that this red, again this blue circle is shifting to the red circle here. So this is just a schematic to show that. Or you can see here the cloud band, clouds or rain bands, which is shifting towards south. So that's why you have more rain here and less rain here. So this is just a schematic to explain the process. And that is one application. And I just wanted to show another application, which is called the modeling the lateral flow of dissolved organic matter, DOM means, in the land surface model, which is a component of community earth system model, that is global land model, and also Norwegian earth system model actually. So just to give a brief definition of dissolved organic matter. So for example, you have tree leaves. From trees you have the carbon which is going into the soils and then maybe to the rivers actually. So if the carbon whatever which is going from trees to the soils and then to the rivers, so basically carbon which is dissolved in the water. So that, so presently in Norway I'm trying to work on this actually. So I'm trying to model this and how this carbon which is going into the rivers and ultimately which is all the rivers, I mean from rivers, how that is reaching the oceans actually. So just to give an idea that the carbon in the soils, this is about like 1600 petagrams of carbon which is stored in high latitudes, like in northern hemisphere high latitude soils. And every year there is about 400 teragrams of carbon which is going into the rivers actually, so water, and then that reaches to the oceans. So but why we want to model this in Norway? Actually this is really important for Norway. So dissolved organic matter actually is linked to the ocean waters. This is because so the carbon which is going from soils to rivers and to the oceans, that is making the coastal waters dark, and then you have a climate warming for that. So then that affects the actually cod spanning, the fisheries. Cod is one fish actually. So one of the fish names cod, which is a famous and economical fish actually for Norway. So this is affecting the spawning of these fisheries actually. That's why so we want to study that. And this project is called Green Blue. Green blue basically means the green, like greenery, the vegetation or trees, which is affecting the oceans actually blue. That's why this project is called and Green Blue, and which is funded by Norwegian Research Council. So yeah, here you just see the climate. So if you see that this is actually there is a Secchi disk depth actually, that means you can see the clarity of the oceans water, or how the clarity is changing of due to the carbon which is going, carbon or whatever the organic matter which is going into the oceans, how that is changing the color of the ocean. So if you see that from 1900 to present day, the clarity of the ocean is decreasing. That means ocean is becoming more dark. And if you see the temperature over that region, over the ocean in that region, there is an increase in temperature. And then there is a link in how the fisheries is spanning. If you see from 1900 to, there is a change in spanning period, like about this is -20 to +20 days actually. So yeah, so there is really about 1 month delay, I would say, in spawning. So that means this really affect the fisheries and their economy and everything actually. So I mean in Norway, the really main economy, one of the main economy is fisheries actually. So just to give an idea, like how we are modeling this this carbon which is going to the oceans. So here I wanted to show that there is a Mozart routing model. This is like model for scale adaptive river transport within the community land model. This is the land surface model I was showing before. I hope all of you may be remembering. I was showing the atmosphere component, land component, uh, ocean component of the global climate model. And here, this is only land component I am talking about, because we are trying to focus on carbon in the land, how that is going to the oceans. So I try to focus on the land model, like CLM, which has the river routing model. So you can see that basically this is an assumption in the model. How we model these rivers, you have like tributaries, like small tributaries. So, or hill slopes, you can say water goes from hill slopes to the small tributaries and then to the main channel actually. So this is like main river. You can say that this is, so if you consider a river network, which is represented in the model is this way. So this whole boundary is like a watershed, if you think. So you have small waters which are from hill slopes, which are coming into the tributaries, and then all tributaries are reaching to the main river. So yeah, you can see here, this is a conceptualized network. So hill slope, all the water goes to the routing network, sub networks, and then to the main channel actually. And this main channel leads to the oceans. This main channel means actually it's a river. So here you see again the mathematics where it comes is, this is the equation that I try to solve actually. This is for dissolved organic carbon. So dissolved organic matter means it can be dissolved organic carbon, dissolved organic nitrogen, or many chemicals which are present in the soils, which it goes to the also rivers. But I try to focus on only the carbon here, dissolved organic carbon. So again, this is again mass balance equation. So what is going into the water, or to the tributaries or to the main channel, and what is coming out actually. And then what is the source of this carbon which is going into the river. So this is the dissolved concentration of the carbon, and this is the stream flow, how much water which is going. So the Q is the stream flow, and this is the carbon. So this is a simple equation to show that. I hope many of you can understand that. And basic idea is to to get numbers like this. Actually, this is the world map. So through this equation and through this land model, so because in each grid cell of the globe, you can really simulate how much carbon which is going from trees into the soils and then to the rivers, and then take that carbon, how much of what fraction of the carbon which is going into the rivers. So you can basically quantify that, and see, you can see that the DOC concentration, like you can really estimate, like over India or over Norway. You see that in Norway, so the concentration of the carbon, which is very high actually. So if you compare to India, blue means almost like 0, or like about 5 milligrams of carbon per liter, which is going into the water. But whereas in Norway, this is about 50 uh, milligrams of carbon per liter, which is going here in Norway. You see that. That's why our project, which is really focusing on this, to understand how much the carbon which is going into the oceans actually. So yeah, there are many basics. I think I don't need to go all this. Just to show here, the y-axis is modeled DOC concentration, modeled dissolved organic carbon, and this is the measured, like from the observations actually. There are a lot of observations people do in high latitudes, so we try to compare the model with the observations. So you can see that, so though there is not 100% correlation, but you can see there is, I mean, there are some correlations with the model, so it's not that bad. Model is similar. If you take the correlation coefficient for this, if you fit the line, I think it's more than 50% accuracy, you can say that. So yeah, maybe I will try to yeah, this is one, this is the more details, like how I model the carbon which is going into the rivers. Maybe I think this is not required. I'll just uh, skip this. Okay, so yeah, maybe this slide is important to show that. So yeah, basically when I you see here how much, so we try to have a parameter from the observations. We try to quantify how much DOC is produced per day actually. So this is the term. And then based on moisture, like in the soils, what is how soil is wet or soil is dry. So based on the moisture and temperature of the soils, so the carbon which is decomposed or which is going into the water, so this is also considered here, like function of soil moisture, function of soil temperature. And then this is actually the function of vegetation, like how much tree leaves fall, that is also considered here. And even DF is actually, this is the term which is for clay. You may even we can consider like the soil is whether clay, or how good the soil is, whether it is just sand or clay, so you can consider that. uh, and then how much the amount of total carbon present in the soils. So this is again exponential function. I think this function is a solution for the concentration diffusion equation. If you any of you remember, or if you do some assumptions and solve the concentration diffusion equation, you may get a function or a solution like this actually. So this is basically that's what I am doing here. So for DOC production in soils, so this is the term. You can really quantify based on all these parameters how much which is going into the water actually from soils. Yeah, here again so I think I try to quantify how much also carbon goes from slow pools to fast pools, like, or from litter to soils. There are different pools here. There are really more details. I think I don't need to go more details here, so I'll just go next. Oh, okay, next. Okay, so yeah, basically this is the final schematic to show that how the carbon which is from the soils in the land model goes to the rivers and then reaches to the main channel actually. So from tributaries, these are the tributaries, that means a small small networks, waterways, and then to the rivers actually. This is the network. So yeah, so for river hydrology actually, to solve how the water based on the the river depth, how deep the river is or how shallow the river is. So all these are taken care in this model actually, which is called Mozart, which is inside this land model actually, model for scale adaptive river transport. So this is the model. I mean, again, this is developed by from several years by many scientists, and people are started using this actually. Okay, this is more detailed network and equations, how actually this is modeled. Maybe yeah, this may give clear picture how I model here. You see that hills from hill slope, like for example, there is a hilly area, hill slope. The water goes from there and to reaches the sub network or tributaries I showed, and then it reaches to the rivers, actually, main rivers. So I solve the mass balance equation, this one I showed before, for each of these hill slope, how water is going and taking the carbon from hill slope to the subnetwork, and then from subnetwork to the rivers. Main channel means actually river. How this carbon is going. So you have three mass balance equations here. I solve. This is from for hill slope, subnetwork, and then main channel. Yeah, these are again a lot of details to tell that what is the flow, inflow and outflow. I mean the lateral flow, how the flow is from upstream to downstreams. Okay, so yeah, when I do the river transport model again, so this only in the land surface model, but this is actually inside the Norwegian Earth system model. It's a global climate model. So if I do coding in this model, land surface model, I was talking about CLM, and then I can really run the global climate model. So the CLM is inside this global climate model, the Norwegian Earth system model. So yeah, again, this is a full schematic. You see that here, even there is urban buildings are also represented in the models. How river discharge, wood harvest, how much wood you can harvest, even crop plants, fire actually, even the forest fires, that is also represented. There are lakes which are represented in the model. Yeah, this is really a complex system which are through equations you can really study the global climate. Okay, yeah, I think, yeah, forget about this slide. Okay, that's a different. So maybe what, yeah, I think I'll try to wrap up. I'm not sure how much time I took. And can anyone tell me?
Sir, you have taken 1 hour.
1 hour? Oh, okay.
Yes,
So
sir.
yeah, okay. Then this is that. Yeah, I'm trying to conclude now. So there's some takeaway messages. So what you can take away to home from this presentation is that generally the models are global climate models produce the simulations of current and past large-scale climates that agree with observations. These global climate models can simulate the climate which is agreeing with the observations. So, and climate models have also produced an accurate hindcast of 20th century climate change. Hindcast means again the past, whatever happened. Climate happened. You can really reproduce whatever happened in the past, like including climate warming and CO2 emissions due to CO2 emissions. So this gives us confidence in using these climate models to project the future climate change. So by looking at the past climate, how the models are simulating, so you can really those models really give us the confidence to project future climate change. And then climate modeling is really already computationally intensive, but increased computing power would allow for more comprehensive simulations. The technology is day by day is increasing, and you have better computers to simulate this globe, so to simulate the globe using these complex models. And in future, maybe if you have good supercomputers, you can really focus on high resolution global climate model simulations. Yeah, this one is to tell that you can really, so in the past, this is one of the result from my paper published in climate dynamics, where we tried to look at how CO2 fertilization, nitrogen deposition, and just the climate warming alone can affect the greenness of the globe. The NPP means net primary productivity, how the trees turn green. So you see that CO2 fertilization, I mean, when you have CO2 emissions, so that can contribute to also CO2 fertilization, which is increasing. You see here the green line from 1850 to 2000. So you see that the plants are greener when you have a CO2 fertilization. Like this, the advantage of this global climate models is really you can really quantify only CO2 fertilization, how much this can affect. So, and then nitrogen deposition, how much nitrogen which is depositing on the trees or onto the soils is changing the greenness of the trees. So you can really separate the effects, and then you can also combine the effect, you can quantify. So this is the real advantage of these global climate models. Okay, with that, I think I give thank you for your attention. Yeah, I'm happy to take the questions.
Participants, any questions?
Okay, maybe no questions in the chat. No. Okay.
Okay. Any questions? Please post it in the chat box.
Yeah, I'm not sure whether this was like how it was, how easy to understand all this. Maybe anyone of you can give feedback.
Okay, sir, it's my great pleasure to propose vote of thanks. I think no questions from participants.
Okay.
I would like to thank you, sir, for accepting our invitation and taking out time from your busy schedule and enlightening us with your knowledge on researching ecosystem, atmosphere interactions using climate models. Thank you, sir. Thank you very much.
Thank you. Thank you also. Yeah.
I thank all the participants for making this event successful. If you have any questions, I'll send you the mail ID. Please post your queries or doubts if you have anything regarding to the presentation what sir has shared with us.
Yeah, sure.
And also I have posted the feedback link here in the chat box. Please do fill the feedback form. Okay.
Yeah.
Yes, sir. We'll wind up the session for today. Thank you, sir.
Okay. Yeah. Thank you all.